I'm happy to introduce the next speaker, Igor Tsiutsiurupa from MRPT, and he's going to speak about functional Lowner ellipsoid. So, Igor, please.
I'm starting. Okay, so hi everyone. My name is Igor, and I'm giving a talk dedicated to functional Lowner ellipsoids. This is the joint work with Grigor Ivanov, and let's start. The contents of the talk are as follows. First, I will give you a quick reminder of what are John and Lowner ellipsoid, but since you have been listening to Atila's talk just a minute ago, you probably have heard about John ellipsoid at least once in your life. Next I will tell you what are low-concave functions. I will explain what is our problem. I'll explain what were the first approach to this problem, and then I will tell you about our achievements in this field. So you are given a convex body in RD. The John ellipsoid of the convex body in RD is the maximal volume ellipsoid contained in this body. And the Lowner ellipsoid of the body is the minimal ellipsoid containing this body. These are classical objects in convex geometry, and here are the pictures of showing you Euclidean unit ball containing in some polyhedron. Here I tried to show you a John ellipsoid of some polyhedron. Okay, so these things, they enjoy many properties. First off, they do exist for any convex body, and they are unique. It's nice. Second, the John ellipsoid of a convex body can be characterized by some algebraic condition called the John's condition, which was proven by John himself and Keith Ball. It says that the Euclidean unit ball is the John ellipsoid of a body K if and only if there are some contact points on the boundary of K of unit Euclidean norm and some positive weights C sub I such that the following algebraic condition holds. This is a classical result. Next type property is that these two objects, they are in some sense dual in the sense of Minkowski's polarity. And it says, this duality says that if you compute the polar body of the John ellipsoid of the body K, you obtain a Lowner ellipsoid of the body that is polar to the body K. Another important thing about the John and Lowner ellipsoid are the following quantities called volume ratio of a body K and outer volume ratio of a body K. The volume ratio of a body K is simply a volume of the body K itself over the volume of its John ellipsoid to the power of 1 over d. And in some sense, dual quantity is the outer volume ratio of a body K, which is the volume of Lowner ellipsoid of the body K over the volume of the body K itself to the power of 1 over d. And an interesting question is, what are the upper bounds for these quantities? The answers were given by Keith Ball and Frank Barth, and they are as follows. The volume ratio of a body K is bounded from above by a standard d-dimensional simplex in the case of arbitrary body K, and by the volume ratio of the standard unit of the standard cube, standard d-dimensional cube, in the case of origin symmetric body K. There are also, in some sense, dual upper bounds obtained by Frank Barth. They say just the same in the case of arbitrary body K, and the outer volume ratio in case of symmetric body K is bounded from above by outer volume ratio of standard d-dimensional simplex. Up to the order of magnitude, these quantities are all square root of d of dimension. So, okay. Another thing to recall is what is log-concave function. Log-concave function is the function on Rd whose logarithm is a concave function. Simply, you can express the function f in this form. Here, the function psi is a convex thing. The most simple examples of log-concave functions are the following. First off, it's just an indicator function of a convex body in Rd. Here, K lies in Rd. This is an important example in the sense that it allows us to somehow embed the family of convex bodies in the setting of log-concave functions. So somehow you can consider convex bodies as log-concave functions, just seeing instead of them their indicator functions. Next thing is like a standard Gaussian distribution in Rd, and probably I guess that any other probability that the probability distribution you will now recall is log-concave function as well. The next important example is the marginal distribution on Rd of the uniform measure induced by a convex body in Rd plus S. And actually, any other log-concave function can be obtained as a weak limit of such marginals. And the question is, can one define a generalization of Lowner ellipsoid to the setting of log-concave functions, and the notion of the John ellipsoid as well? I'll tell you why this is interesting. Actually, in the past few decades, it is a trend in modern convex analysis and asymptotic geometrical analysis to transport the theorems about convex bodies in the setting of log-concave functions. Just because the example I've shown you before, you have seen that an indicator function of a convex body is a log-concave function. So you could think that you can just try to formulate some results about log-concave functions in terms some results about log-concave functions if you know some theorems about convex bodies. So, and humanity have succeeded in this field. Actually, there are some results of this type. First to my mind is like a functional Santallo inequality by Arstein, Avidan, and Milman, and millions of such results. So how does one define a Lowner ellipsoid of a log-concave function? First attempt to this problem was done by Ben Lee, Carsten Schutt, and Elisabeth Werner a year ago. And what they have thought of was the following. You are given a log concave function on RD. So now let us consider the log concave function of this form. And then among affine positions of this function, which are the functions of this form, here A is just a vector in RD. Capital A is a non-degenerate operator in RD, linear operator, and alpha is a positive scalar. Among affine images of this function, namely the functions of such a form that are pointwise at most the function f, find one of the minimal integral. Well, you may recall that in convex setting, you were given a body and the Euclidean unit ball, and you were looking for an affine image of the Euclidean unit ball containing your given body K. Here you are given with a log concave function, and in the family of affine positions of such a log concave function, you look for the one that is pointwise at most f. It means just it contains f in its subgraph, and you're required to be a minimal integral. So this optimizational problem indeed has a unique solution. The solution is the solution to this problem. It exists, it is unique, and it is what is reasonable to call the solution to this problem the Lowner function of your log concave function f. So this is what have been done by these three authors a year ago. The dual problem of finding in some sense, dual problem of finding the John function of a log concave function f. This problem was solved 2 years ago in 2018, if here you are looking for like an affine image of this thing that is pointwise at most f, then those authors they were given a log concave function f, and they tried to find an cylinder in the subgraph of your log concave function f of minimal volume. So roughly speaking, this is what dual problem is, and the solution to this problem exists as well and is unique, and it is what they are calling John function of log concave function f, just simply a characteristic function of this ellipsoid times this height. And this optimizational problem is dual to that I just explained to you. And this is the preliminaries to what have we done together with Grisha. Why not ask for more? Again, you are given a log concave function f, but now instead of just simply e to the minus Euclidean norm of x, you consider just an arbitrary radial log concave function, which has to be of the form e to the minus psi of a norm of Euclidean norm of x. Here psi is just arbitrary convex function, and this is what should be a radial log concave function. And among the affine positions of a radial log concave function that are at most f pointwise, you look for the one of the minimal integral. Okay, so well, the geometry behind this problem is that these things are, well, they are log concave functions, and its superlevel sets, they are concentric ellipsoids. By the way, in case you choose, like, instead of the function psi, just the identity function, you fall into the Lee, Schutt, and Werner case that I just considered. few slides ago. And in case of like psi equals to 2 squared, you look for this covering log concave function of minimal integral that is a Gaussian function. So if you here, instead of psi, write just x squared, you look for a Gaussian distribution that is at least your log concave function f pointwise, and that is of minimal integral. And well, this optimizational problem of looking for this covering affine position, the solution to this problem exists if, for example, if the function psi is strictly increasing convex function. So the solution to this optimizational problem is what we call the Lowner function of your log concave function f. So the solution to this problem exists if you can cover the function f with a affine position of this form. If there is at least one position that is pointwise at least f, then the solution to this problem exists and is unique. And more of that, we have an upper bound on the supremum norm of the solution to this problem, which is like e to the d times the norm of f. So that's it. Here is also an interesting particular case of the function psi that I've just considered. If you pick like a positive parameter s and choose this ugly looking psi function, never mind it's ugly, never mind that it is looks very awful, it appears to be very interesting because the problem of minimizing this integral, yes, is in some sense dual to the problem of maximizing integral of such a function subject to the restriction that it is at most f pointwise. So the problem I'm considering here in this talk, in some sense, dual to that considered by Ivanov and Nasodi this year, and the solution to this problem also exists and is unique, and it is what they call the John S function of the log concave function f. And this is in actually very nice generalization of the notion of John ellipsoid, simply because this the solution to this problem can be characterized in terms of John's condition. It can be characterized like in terms of algebraic condition that looks just like John's condition. So this makes this problem extremely reasonable, and the problem that I'm telling you about here is dual to this one. So this gives me the reason to say that it is all very cool. So the next important thing is that, well, recall what the outer volume ratio of a body K is. And if again we roll back to the Lee-Schut and Werner Lowner function of the function f, we can define the following quantity that is a reasonable generalization of what outer volume ratio is, but in the setting of log concave function, and what we did is giving the asymptotically tight upper bound to on outer integral ratio of a log-concave function f. It is just a generalization of the result of Frank-Barth, but in log-concave setting. So this bound is asymptotically tight, as you can see putting here an indicator function of the standard cross polytope. So this will give you the order of magnitude square root of dimension, but and well, it's nice. It's very nice. So now I'm giving you ideas of the proofs. When you are proving the uniqueness of John ellipsoid, of Lowner ellipsoid of the convex bodies, or in our functional case, the uniqueness of this of a solution to our optimizational problem, well, we all can follow the same ideas, the same track, I'd say, which is the following. First, we interpolate between two ellipsoids or two ellipsoidal function. I mean that given two ellipsoids or two ellipsoidal function that are contained, say, in the body K, you learn to construct a third ellipsoid that is contained as well in your body K. Next, using Minkowski's determinant inequality, you can show that this new constructed ellipsoid has the volume at most that of these two guys. So after some thinking, you came up with the idea that if there are you come up with an idea that if there are two ellipsoids of maximal volume within the body K, then they have to be translates of one another. Then, you can construct third ellipsoid that is of strictly bigger volume than these two guys, and you're done. Actually, this route can we can reconstruct this all these ideas to prove that our Lowner function of a log-concave function is unique. Just following almost the same lines with some non-trivial steps, but generally the idea is just the same. Next, the existence of a solution. Well, it is also proved in the same way that the existence of Lowner and John ellipsoid is proven. First, you bound the parameters of your optimizational problem. Then you recall that the set of these parameters lives in a finite dimensional space, and this yields you the compactness of the set of your parameters. And then this immediately implies that extrema are attained. The maximal volume ellipsoid exists, the minimal ellipsoid exists, and the Lowner function exists as well. The pearl of the talk and of this paper actually is the upper bound on outer integral ratio. So let me tell you the sketch of the proof. So now I'm going to tell you how this upper bound was obtained. But first, let me explain you why it is interesting, actually. Well, it's not a secret that any log-concave function f can be bounded from above by a function of this form. I mean that for any log-concave function f, you can find some constant theta and v such that this inequality holds. And an interesting thing is to try to find this upper bound that is of minimal integral. And what is the upper bound on this minimal integral? Well, actually, if you write something like this, like theta e to the minus vx, and then you integrate this, then this inequality implies that the upper bound on the minimal integral, such that this inequality was true, is like some constant times d to the d over 2. So I believe it is a very nice illustration to this outer integral ratio upper bound. So what is an idea of the proof? Well, first you notice that this ratio is an affine invariant, just like the outer volume ratio or just the standard volume ratio. So the trick is to find a convenient position of your low-concave function f. So by affine invariance, I mean that this ratio does not change under affine change of coordinates and scaling of your function f. Well, this is clear from the definition of Lowner function, but to make it more precise. So the trick is to find a convenient position for your function f. Next, well, I'll explain you what is the convenient position. Well, you can move your function f in such a way that its maximum is attained in the origin, and scale it in such a way that the maximum is e to the minus d. These are just like some technical details, and this lets you find the minimal integral function of such a form, yes, that is pointwise at least the function f, and without any loss of generality, you can assume that this operator a here is the identity operator. Just simply change of coordinates does the thing. So since you have this upper bound, yes, you conclude that the outer volume ratio of a low-concave function f is at most this fraction. Now a very ambitious problem arises. How can we give a lower bound on the integral of a low-concave function f? This is just an arbitrary low-concave function, and you try to find a lower bound on its integral. How does one do that? A problem of a century, actually. So here's the idea. Here is your low-concave function f. It's subgraph, and a subgraph of e to the minus x. So actually, low concavity is a very strong restriction on the function. Well, it plays here something like this. If you try to slice your subgraphs with like hyperplanes in our d+1, yes, namely to watch the superlevel sets of your low-concave functions, you see the following. Actually, the superlevel sets of the function f, they are, of course, contained in the superlevel sets of the function e to the minus x, which are centered Euclidean balls. And clearly, you obtain such an inclusion here. Of course, because these blue guys, these are just the, the level sets of e to the minus x. These, they are just simply Euclidean union ball, yes? And they have the level sets of the function f contained within them. Okay, so here dividing this inclusion by R and taking the union of such a sets with positive R at most D, I can construct a body K sub F of the following form. Simply, you just fix your unit ball here and put here sized versions of superlevel sets of the function f. You put them in this Euclidean unit ball and construct this body K sub f. What is interesting about this body K sub f that we have never actually seen it in the literature, but here is the idea. This body KF is the minimal volume ellipsoid that contains, I mean that the Euclidean unit ball is the minimal volume ellipsoid containing this body KF. Just because watch the way this body KF been constructed. All its like bricks are contained within Euclidean unit ball, and just due to this restriction that e to the minus x is the minimal integral function at least f, it follows that the union of these superlevel sets, they are all contained in Euclidean ball, and the Euclidean ball is the minimal volume ellipsoid containing this body. Well, then you can recall the John condition for the Lowner ellipsoid, which is looks just the same as the standard John condition, and this allows you to inscribe simple exponents in the subgraph of the function f. Remember, you try to bound the integral of f from below, and due to log concavity, you can inscribe here in very specific way pieces or just the whole exponent under the subgraph of f. Yes. Then the magic goes on. Then you recall reverse Braskamp-Leib inequality proved by Barth 20 years ago, which is here has very impressive form, and is I believe that here at most 4 people ever seen this inequality, but it is very nice and have led to few great results in convex geometry. And using this Braskamp-Leib inequality, reverse Braskamp-Leib inequality by Barth, and log concavity of f, well, we deduced that the integral of f that was put in such a special affine position is at most e to the minus d. And this solves our problem of finding an upper bound on outer integral ratio of a function f. And actually, that's it. That is everything I was going to tell you today. And well, thank you for your attention. Any questions are welcome. Sasha, I can't hear you if you are saying anything.
Thank you, Igor. Do we have questions?
Okay, I might ask one.
Okay.
What happens with the duality?
What do you mean by happening?
I mean, what is the relation between Lowner ellipsoid and John ellipsoid?
You mean classical objects or?
No. Here for log concave functions.
Well, okay. originally, the problem was as follows. Well, you and Martin Nasoli, you were considering the functions of such form. Yes. And you were given, well, I do not tell you how these functions actually were built and for what purpose, but I mean that they are nice to
This is the marginals of the unit ball and higher dimension of S integer.
Okay, this is a nice description. So looking for a function that is at most f pointwise of maximal integral. This is what you, Grisha, and Martin were doing. So the duality here is the following. What we were doing in this paper is considering dual functions to functions of this form and dual to like this guy, which reverses the order and makes us consider the functions of this form at most f and its affine positions. The duality is formulated for low-concave functions in a very similar way that it is given for convex functions. I give you a brief reminder that if you have a convex function psi, you can construct its Legendre transform.
Okay, but I didn't ask about definitions. I mean, just you mentioned duality already in your talk. Do you know anything about that? There is, I mean, perhaps it's one shouldn't consider the dual problem because if you settle one, then another is just the dual statement. Yes, and
yes, although you can actually formulate what should be a dual problem, there are no tools to obtain.
What is the decision? I mean, why it's not just a dual problem? Is there any problem with this?
Yes, there is a problem because, well, although let me show you a slide. This slide where I've been talking about this. So here for in the classical convex setting, there was a duality. If K is like it contains 0, it's interior, like in this case. Here, then you have this duality.
It's not true. It's when the center of the ellipsoid is in the.
Oh, sorry. Of course, I mistook the ellipsoid for the body. Okay, sorry. It's just yes, of course. And in the case of, say, Lishut-Werner case, if you consider the functions of this form and functions dual to them that are just the indicator functions of ellipsoids in RD, there is no duality for Lowner functions of Lishut and Werner and the constructed John functions of low-concave functions. In this, like I'd say, primitive case, there is no duality already. So in our case of like psi s functions, there is no duality as well. We believe that there is a counterexample for any positive s, and the counterexample was given for these guys in the paper of Lishut and Werner.
And what happens for Gaussians? Have you studied this? I mean, personally, you.
Well, in our paper, the Gaussians are studied in the following sense. Sorry, just a second.
No, I mean about the question about duality. So you have one limit that S is 0. Okay, there is no duality. Okay, probably for even function there is duality, but for general curves there is no duality, and probably in somewhere in between, when S is bigger than D, then there is a duality between S functions. Or what happens in infinity case? So in infinity case, I can say that in setting of the Lowner functions, there are always, if you can cover a low concave function with a Gaussian, then there is the best one, unique best one. But in for John functions, for John Gaussian, so if you want to inscribe a Gaussian under the graph of low concave function, that it's not unique. Yeah, it's not necessarily unique, and but it seems to me that so what is your opinion on this question? So do you think that there is a duality in infinity case, at least some kind of duality, or what? Or it's not? There is no duality in general for any S.
Well, I hope that the minimal integral Gaussian in this particular case here, that its polar is the Gaussian as well, and this is clear, and its polar might be a maximal integral Gaussian that is pointwise at most your low concave function, but just as you said, the maximal integral Gaussian under the subgraph of f is not necessarily unique. So it is interesting.
Okay. So thank you, Igor. Thank you very much.
Thank you.